Hi, my name is Gerhard. Um, I'm glad I can show some of the nanoHUB aspects. What I like to do is give you a bit of two different views. I'll dive in and walk you through some tools that I like that you might find interesting, and then maybe we can open up at the end for questions on things that you like to explore. But I'll start out with sort of giving you an overview of how maybe NSF and other agencies and how we look at nanoHUB as a platform. So let me share my screen here. So let's go here. So some persons might have seen some of this before. I apologize. This is sort of my overview of nanoHUB as a platform. So who's there? It's about 2 million users annually, and we have a cool animation of sort of activities. This thing doesn't sleep. It doesn't run out of the corner of my lab. It's really become a national infrastructure that serves the globe. And it's kind of instructive to see this as a static view as well, where you can basically see in a year's worth of users, we cover the globe. There's lots of interest in nanotechnology and learning about it and using it in a variety of different ways. And I like to start out with the inspiration. Why did we build it? And we started out quite a while ago, and the inspiration starts from a really global investment in the United States, a specific investment of about $2 billion in nano research, where lots of software and data is being generated. But in general, this is not available to a broader audience. There's lots of artifacts that are generated, but they're not accessible. And we created nanoHUB such that these artifacts become real resources that are usable in apps that now have a global impact. So that's really the nanoHUB inspiration of an opportunity of knowledge generation to convert that into something really useful for a broad audience. The vision really is then to have an accelerated innovation through user-centric science and engineering, not just high-end research, but enable a broad audience and really provide products that are engineering and science products that are usable, discoverable, they're reproducible, and easy to create. And we do this for learners, educators, researchers, and business professionals. So if you look at a center, there's an inspiration, there's a broad vision that sits out there that you may or may never really achieve. But then there's a mission of the stuff that gets us up in the morning to make us do the work we do. And that's really creating products that are useful. That being said, what is it? So we have about over 600 apps that are running in the cloud, and I'll give you some examples. There's over 5,000 lectures and tutorials, over 110 courses. And there's a bunch of people using them, typically students and faculty and industry practitioners. It's an infrastructure that really operates 99.4% uptime. That means it's really down only a few hours in the year. And we measure impact in a variety of different ways. We certainly look at research. And as of 3 years ago, the nanoHUB tools and apps are now listed in the Web of Science and in Google Scholar. So they've become new types of publications, no longer just papers, PDFs, but really the tools are becoming publications. And we track citations in the literature. So there's been over 2,500 papers now that cite us. And that was really done to show that you can use a site like that for research, because many people had the perception you couldn't do it. So we changed perspectives. And the perspective was you can't use this for research, and we can prove them wrong now. And similarly for education, people thought you have to create something special for education. You can't have research outcomes that flow into education. And we can track now students in classrooms. We can track the classes, and I'll talk a little bit more about that. And we can change curriculum. And the bottom line is that we're changing how people think about some of these problems, and we're changing the underlying assumptions. And that is what's called a paradigm shift. It's a shift on people's thinking. And that is how we look at nanoHUB, and that's how I present it to funding agencies like NSF that is really has been supporting this. So going from here, I want to motivate it from a more practical sense. And I go back, way back in time, of a really cool, innovative capability. This is the first car with a combustion engine. Quite old. It had really cool features. And it had also a bit of a couple of handicaps. What really made this car impactful was a new innovation of making it usable and accessible. On the top, you had to be pretty rich to to use this thing, and there were a few. And Ford really created a mass production of usable and accessible tools that came out of that innovation. And similarly, you might have seen, maybe you're too young, but these tablets PCs have been out for a while. And then when these iPads came out, people said, well, we've had tablet PCs. Well, the issue was you had to read a 200-page manual before you could actually use that tablet PC. And if you have a 2-year-old or 3-year-old using an iPad, obviously the usability is surpassing maybe a higher capability of this more powerful computer. But if you can't use it, or you have to, there's these huge obstacles, you really don't have the impact. So similarly, on nanoHUB, we have these tools that are reasonably well known. They may not mean a whole lot to you, to this audience, but they're engines, they're complex tools that have been developed over the years. And they do a variety of different things in nanotechnology and material science, but they're really unusable to a broad audience. And they're kind of similar to this. If you want to use some of these tools, you have to be like me, the big fat guy in the back that has a graduate student. And that graduate student has the X-term at his fingertip and can operate these tools. And it runs on the supercomputer. And that supercomputer is expensive, and you can't get access to it unless you're really rich. So these software packages are kind of similar to this first card. And what nanoHUB has done, it has put interfaces or apps around these tools and made them accessible and put them into people's hands. And are they as powerful or sophisticated as the underlying engines? No, the apps are simpler. They can only do a certain amount of things, but many more people can use them. So that's really the key insight here. So with that, we made these tools interactive, and we've seen significant nanoHUB user growth once we made these tools interactive. I mentioned the Web of Science. And for my own research, I built these NEMO tools that literally are being used now at Intel to design 5-nanometer transistors, but they're also being used on nanoHUB, and I'll show you some examples of how people can use them on nanoHUB without having to have their own supercomputer. So, so that gets me to usability on tools, and here is an example of a slide that I showed a long time ago. There's a tool called Padre we actually got from Bell Labs. That tool designed transistors, the older style transistors of the year 2000, 2005 or so. It's a full-fledged tool, and in order to use it, you have to speak this gobbledygook language that you have there. It's actually pretty structured, but it's still a language that you just don't speak. But so we have this tool on nanoHUB, we embedded it, and we have nice graphing that comes out automatically. So that's kind of cool. And we have users on this. But we also have this kind of tool, which is wrapped around this engine. And this If you're familiar with a MOSFET that structurally looks like a MOSFET, you can design a transistor, a simple transistor like this, and without speaking the gobbledygook language. And here's a comparison where we built 6 of these apps around this complex engine. So in 2010, we had 900 users on the complex engine, 6,000 users on these 6 apps. Today, it looks quite different. We have 2,500 users and 40,000 users on these apps. So it really, actually, the data is a year old now. But the point is, it's really in making this accessible, usable to more people such that they can solve their own problems. So we've seen the importance of a GUI like that, where in the early days, early days, when I joined nanoHUB in 2003, we had apps that looked like this. This is kind of what your bank still has today. You can fill out some numbers, click go, and you get a query and you get a static graph. You can't do much with it. And we converted that into interactive apps. And here we have data showing up to 2005, where we have some users, and then there's a couple of poor suckers in the classroom that were made to do some homeworks. But the point is they didn't come back. Once we made the tools interactive, we've seen dramatic growth. And as a counter correlation, we really have a dramatically reduced number of source code downloads. So people aren't really interested in downloading software. And the few people that used it typically also downloaded it because the user interface wasn't all that good. So the point is really it's usability that's important in getting it into people's hands. All right. So you're too young for that. When the iPhone came out, I think 2007, people said, oh, terrible phone, ARM processor. We have much more powerful phones. iPad, oh, terrible processor. We have much more powerful computers. And they changed how we use the internet. They changed how we use apps. They changed how we communicate. They literally changed our life. So it's in academia, we often look at capability of raw, what can I do in principle? We don't think about what will I do in practice? And that's where nanoHUB comes in. So what do people do? So here's a way where we can kind of figure out what people do. And on the horizontal line, you have time. And vertically, I'm stacking individual users that come on a specific day and use a particular tool. For example, here, there's this purple tool that's sort of used in a rhythmic pattern throughout a whole semester. That's one group of people using the purple tool. Here's another group that uses 1, 2, 3, 4, 5, 6 different tools throughout a semester in a rhythmic pattern. And here's another group, different tool set. I can actually measure classroom size by people behavior, which is kind of cool because in general, some students don't even know why in the world are they coming to Nano? Well, my prof told me to. And they have no clue what they're going to do, and they don't even necessarily know how to answer the question that we asked them, why are you here? So we try to figure some of these things out and actually document the use in classrooms. Now, you can do the flip side now is, well, these are tools that are used in education, right? This purple tool here is used in education. These 2 different green tools are used in education. So I can rank these tools on some sort of vector, which means 0 might mean no use in classrooms. 1 might mean very heavy use in classroom with lots of students. Many classrooms, many students. And each dot here now is not a person anymore, it's a tool. I mentioned to you that we also measure impact on research, where we can measure the tools as being used in research. And I can rank them in terms of 0 use in research to heavy use in research. And my peers think, and used to think, that you're either creating something for education or you create something for research, but you couldn't create both. And Believe it or not, they give me homework assignments. Like every year we have a site visit, and at 5 o'clock or 6 o'clock at night, they give me 10 questions. Our team, of course, me as in, it's the royal we. And one of the questions we got about 10 years ago was, all right, you have 121 tools. Which ones are research? Which ones are education? Because it truly was in their mindset that you're either one or the other, and please figure out who you are. So that's why I started to develop these analytics. And today I can measure that these tools are actually both used in education and in research. Not all of them, but there are some tools that are used in both sides, which is a kind of a cool thing. So you really have dual use in research and in education. And I can do one more. I can actually look back in history. I can say, well, if I look back in my data that I have from 2001 onward, I don't know what the tool is going to look like, how it's going to be used. So I can put it in the origin, no research use, no education use, and I can let time take on, and I can monitor the use and measure it. So early we had a few tools, then NCN, the organization that I now lead, started. We changed from static web pages to what we call Rapture, which made the tools interactive. Suddenly we can get many more tools much faster, and more people use them. And you can kind of see where they come from. They come from early research use, and then they trickle towards education. And you can really see how education is fed from research results and from research tools. So you should never think of a separation between those two. And if you're at a research university like I am here at Purdue, it's our duty to connect our research results into advanced education and to change curriculum. And nanoHUB really is a platform to do so. So that's the framework as to why we do this, and the inspiration really, and we can now measure it. We can even measure sort of time to market, if you will. How long does it take for a tool that has a digital object identifier, a birthday, to show up for the first time in a classroom? I can measure that time to market or the adoption from research publication into classroom. And I can measure that against the typical textbook time of about 4 years to write a second edition. We have tools that show up in weeks in a classroom after being published. And the median time is less than 6 months. So we can really change curriculum and how we teach rather fast. So that's the nanoHUB story. We created nanoHUB to really convert research results, specialized knowledge, specialized tools into something that could be a product. And now it's my chore to try to show this to people who might not have seen it, and find out what works, what doesn't work, and to make these products better, and to scale it up from what we do currently to areas where we don't really have the expertise, and bring in other people that want to use and create. So that's sort of the nanoHUB spiel, if you will, of telling the story. Why are we doing this? What are we trying to achieve? And how do we measure success? Okay, so despite all these cool slides, right, this might still be totally useless to you. So let's see if we find some examples that might inspire you. Oh, maybe I find some tools. Let me give you a couple of examples of tools that I like. And then maybe we can look at some examples that you have found and that you like to explore. So here's nanoHUB's homepage. I logged in. We really are trying to do modeling and simulation for teaching and learning. We want to enable people to develop the software as well, and then to share it and publish it. So that's kind of at a high level, the mission statement, if you will, on the nanoHUB homepage. And so just like in any good cooking show, I put something in the oven for you already. So here is a quantum.lab. Let me see if I can pull up also. This is, every tool has sort of a publication page. So here is the authors. It has a version number, it has a DOI, has a couple of screenshots, an abstract. There's some basic usage statistics on about 8,000 users, 17 citations in the literature, some 31 questions, some 13 reviews, 6 wishes on how to make this better. So we're trying to engage the community. But in principle, these are independent publications where the authors may or may not be willing to interact with users and answer questions and all that, right? It's kind of a public forum, a public publication. So if I go into the tool here, this one is an example that's actually run on Nemo 5. The idea is to run simulations of quantum dots. Quantum dots are sometimes described as artificial atoms. So if you've taken a course in quantum mechanics, you might have calculated a particle in a box problem, like a cuboid here. So you might have a rectangular box of sorts, and you can calculate eigenstates and optical spectra. So I'm just launching this tool just to give you an idea. So this should run right here. This is the prior run. I wanted to also show you a pyramidal dot. So let's see what it comes up with here. Hello. Now, why am I frozen? This is called Murphy's Law. Let me switch screens once. No, it's still thinking. Let me launch the tool one more time.
Dr. Klimek, I had a question. From like your slide from your PowerPoint, how did you gauge the 0 to 1 values for research and educational use?
It's an arbitrary scale you come up, right? You come up with a metric where you ultimately develop a norm, right? Where even if you had one specific tool that, just for argument's sake, serves 10,000 users, and some tools that only serve 100 users, you try to compact it into a scale from 0 to 1, right? It's just coming up with some metric. It's an arbitrary number, 0 to 1, right? And it's composed of components of number of classes, number of students in the classes, and number of institutions in that use it, right? And frankly, I don't know the formula offhand. I'd have to talk to one of the core developers of that and actually look at it. I look at it sort of like a Google ranking, right? Where some abstract way of measuring it. Launch this tool here one more time. But that's a very good question. I mean, it's in a lot of these metrics, it's not necessarily so important how you get the quantitative number, but how these numbers compare to each other. Does that make sense?
Yes, thank you.
Sure. All right, let me try the cuboid here. I don't know what. I don't know why this guy is still thinking. We'll let it think. So here we go. So here's your box. If you ever seen a particle in a box, you've seen an S-like ground state. And then you might have a P-like. And if this axis here is bigger, then you have a PY in this case. And there should be a PX. And then should be a PZ. But actually, if that box is very thin, like it is, you actually have a combination of PX and PY first. And eventually there should be a PZ coming out. So you have the 3-1, 3-1. So what we would have to do is actually make this box taller. and more symmetric. So this box is pretty flat. So 10, 10, 5. Let's make this 4, 4.5, and 5. And let it run it again. So this solution you can actually do analytically, right? This is this typical standard problem that you have in a quantum mechanics course. And I'm just pulling that up to demonstrate that you can do something like this and compare it to analytical results. But the more exciting thing is to then compare it to structures that you couldn't do analytically. And you will have, for example, if you have some knowledge on quantum dots, you know they actually come in pyramidal shapes and dome-like shapes. And there you really are, can only do an analytical, a numerical answer. So here's your PS orbital, small dots, and then there should be, here we go, PZ, PY, PX, right? Just like what you expect to see if you've done a little bit of quantum mechanics. And then again, you get, it's called 2 by 2 by 1, right? These you could also label as 1, 1, 1, quantum number, 1 in X, 1 in Y, 1 in Z. And then you can do, well, let me call this 2, 1, 1, meaning there's 2 nodes in one direction and exactly 1 node in the other 2 dimensions. So 2, 1, 1. The other one would be 1, 2, 1. And the other one would be 1, 1, 2. Right? So the standard stuff you would expect if you do some quantum mechanics in a particle in a box. Now, and then you could calculate transition energies between these eigenstates in an artificial atom. So you can look at the absorption of light, and here we are. You would have transition energies and absorption between the ground state and excited states, and depending on what states are occupied, you might have absorption. But the really cool thing is you can go in here and then look, for example, at more complicated thing like a dome, like a pyramid. And let's do this one. This is fine, 5, 4.5, 5. That's pretty symmetric again. We should seem rather similar things, but actually now the symmetry of the structure has changed. So in the Z direction, things should look different. They shouldn't look the same anymore. Z is the growth direction of the crystal of these quantum dots. So let's see, what does it say? It actually, yeah, it's running the tool right now. It's submitted pretty complicated input decks. I plotting something that I usually don't show so much. So normally when I do standard simulations, we often have results stored already. So here's my, going here, here's my pyramid. So here's my pyramid. Let me zoom in. Wrong way. So here's my pyramid with the ground state, and looks similar, like there's a px here and a py. And let me make the whole structure bigger, because here this is atomized. Actually, under the hood, I should not have done this for such small structures. What really happens under the hood is what happens under the hood is you have atoms, right, that are really making up the structure. So you're actually starting to resolve some of that numerically, and that's why you see not a continuous wave function, but a discrete wave function. So should have cooked up something slightly better in my original simulation, but that one seems to have been frozen. So here is now my pyramidal dot. Looks much more continuous because I have many more atoms that are making it up. And here is now the excited state. It goes in the diagonal. It uses the virtual space in the diagonal more rather than being aligned in X and Y. So the other state is also aligned now in the other direction. And the next excited state looks kind of cool. It actually sits in the apex of the pyramid with a circle almost around. It resembles like a PXPY, PZ state, but the lower branch is actually split into a symmetric ring, kind of symmetric ring. So you can design your own atoms, so to speak. You can design your own atomic states, if you will, and your own spectrum. And that gives you an idea of some of the visualization you can do. And what is kind of cool is you can, in this framework that we created with Rapture, you can compare different results. So this is what I just ran. This is what I ran previously. This is what I ran first. And I can compare all of these simulations by clicking through these simulation runs. So you can ask what if questions. For example, if I hadn't danced around and made such dramatic changes, I might have been tuning this line to get up or down a little bit by changing the size just slightly rather than what I would call wildcatting of jumping between dramatically different simulations. So this is a NEMO tool, and it, just to give you an idea, in order to run this from scratch, you would have to speak this NEMO language of really setting up a problem, etc., which of course would take a week or 2 or 3 or 4, or a grad student a couple of months to speak the proper language, right? And here with an app, you don't need to speak that configuration language for this tool. So if I now go into another tool, which is what I highlighted before this Padre tool, here's something that most electrical engineers might have seen. It's called a PN junction. It's a really fundamental element in most, almost, well, really all semiconductor circuits. That is a fundamental element where you have p doping, you have typically a sharp transition between p-type and n-type doping. And if I just hit simulate on this tool, it should pull up stored results, because this is sort of a demo instead of recomputing things. And you would get band edges. So here's a conduction band, here's a valence band, here's a Fermi level. And you can, as a function of bias, you can now apply a voltage between the P and the N-type. And you can kind of see that at zero bias, there's a pretty big gap. There's electrons here, there's so-called holes here. And as you reduce this barrier, electrons will start to flow over this barrier here, and holes will flow this way. And you basically have electron flow that turns on in a nonlinear form. As you increase voltage, there's a little bit of flow, and eventually you have a very strong electron flow. That's a typical thing of a rectifying diode, which is what this PN diode is. And you can look into internal quantities like electron densities and hole densities. So you have a ton of holes here and electrons. And as you increase the voltage, there's more electrons getting into the so-called junction area. So you can dive in as a student to understand this device, and then you can ask what if questions, as in what happens if I make this doping stronger, and compare this. I'll get a very different PN junction where it has very different internal properties. So if I compare this to this, you can see this is much sharper now. The Fermi level getting closer to the conduction band edge here compared to this, if I put it all on the same. So really this went down. This is what happens when you have very heavy doping in a semiconductor. So you can explore kinds of devices like this. Now, these would be tools that are somewhat near and dear to my heart. I can show you some nanowire tools on how to design nanowires. transport in nanowires, but maybe it's better if I ask you what are the things that rock your boat, and maybe there are some things on nanoHUB that you might find interesting, and I can maybe give you a demo, or I can say I don't know anything about it, but I can find out more about it. How's that?
I think those are good. I mean, I definitely understand the whole PN junctions because I'm electrical engineer, so we've done PN diodes and learning about different things like that. So this is all up my alley. But I know, is there like anything about like maybe like nano, like in the magnetic kind of
Yeah.
sort of thing frame? Because I'm taking a class about.
That's not my, in principle, my cup of tea, but let's see what we find here. I know we have some magnetics and spin tools here. So there's a tool framework. It's called UMF. I pretty much just know it by name, but it allows you to do micromagnet simulations. So you can have arrangements of magnets and figure out sizes and shapes and what the surrounding electromagnetic fields might be. I have not used that tool, but that's a well-known tool in that community. So we're hosting that tool, and there is a couple of example notebooks that run inside Jupyter. I'm not sure if you're familiar with Jupyter, but we run Jupyter instances where you can basically do Python programming and tie together different tools, or call, for example, this UMF tool out of Python. And I know it needs shape generators, and generating the shapes, just like in several TCAD tools, is often a nightmare. So there's a tool that helps you generate those shapes. So that's in here. And then here's something about an analytic spin precession simulator. So it looks at Hanley effects, magnetic resonance on nanoparticles, multi-physical equilibrium of materials, free Gibbs energy and phi pi, magnetic tunnel junction lab, quantum dot quantum computing simulator. That's interesting. It's in principle up my alley. Quantum point contacts that are magnetic dependent. You can look at channel effects. That's more a transport thing. And then spin coupled quantum dots. So there's a few magnetic oriented tools. And what we've done here is really generate sort of group, we call those group pages or landing pages. There may be other magnetic tools on nanoHUB that I'm not aware of that haven't been captured here. So there's simulation tools, and then it comes with support seminars and some compact models and some experimental work. So we're trying to collapse, or say, if you call it, have editorial privilege to deliver some of these tools, so you don't just blindly search. And if you frankly need to search on nanoHUB, I would say do a Google search with nanoHUB. You'll be more likely to find the resource than doing it in nanoHUB. I'm not very happy about the search we currently have in nanoHUB. Does that give you a bit of an answer?
Yeah, it does. It's honestly, now that I see these tools, like actually kind of relates to some of the things I'm learning about in my biomagnetism class. So I'll have to let my professor know about these and show him.
There's a whole segment of bio nano type things. There is a center that is run out of IU, and let me see. Featured here. There's a whole center of nanobio that is creating content for nanobio type simulations. So they have a bunch of COVID stuff, deep learning with machine learning, etc. So that might be interesting too on the nanobio side.
There's some really good recorded sessions in nanobio and some upcoming sessions as well, if any of the students are interested.
Oh yeah.
All right, thank you for all those. Did anyone else have any questions on tools they'd like to see, or just, I don't know, any questions that you have for Dr. Klimek?
I have a question. If I'm doing like a molecular dynamic simulations, and I'm wondering if I use this website, how many number of particles that you can simulate and how long it can
Oh, yeah.
simulate.
So so we have a bunch of MD codes on nanoHUB, including lamps,
Yeah.
which is sort of the standard code. You can run that inside Jupyter from Jupyter, and there's some. Let me get you there. Come on, simulate. Tools for experts, materials. So here is lamps and machine learning for material science, TensorFlow tutorials, etc. To be concrete, we have compute power under the hood, but I also know that any of the MD guys can suck up any compute power you can ever throw at them. It's kind of an abyss. So I'm not an MD expert. I would suggest you can try to run it through a couple of examples here, run it via Jupyter. Unless you are running a billion atoms, I think you might be well served. If you run 10,000 simulations, you will not be well served. You should apply for a grant at National Resource and run on Exceed. But if you have a few simulations to run with simple interfaces, I think this is the best way to do it that's out there.
Okay, thanks.
Does anyone else have any other questions? Things they want to know?
I was actually wondering, besides the nanobio seminars, are there like any nanomedicine researchers that reach out to you to ask about specific tools that might be beneficial for their work?
There is actually a nanomedicine hub out there that's run by NIH that hosts nanomedicine data.
Oh, wow.
But I would say I don't think we have a whole lot of nanomedicine content on nanoHUB other than these COVID type viral simulations. But I know that NIH runs their own hub on nanomedicine, and I can connect you to it. If you send me a note, I just have to Google it or connect you to the right person. So that exists. I would say nanomedicine is one of these areas that nanoHUB really hasn't had a historical expertise, right? And you kind of need to have people that want to contribute, right? So electronics, optics, photonics, magnetics have been sort of, materials have been sort of our home expertises, right?
Okay, thank you.
Oh, you're welcome.
All right, well, if anyone does have any other questions, I'd like to say thank you so much, Dr. Klimek, for coming out, spending some of your time to kind of explain to us what nanoHUB has to offer, and just being able to kind of show us some of the different types of tools us as students and undergraduate and graduate students can use in the community of learning. I think there's a lot of potential to do research, at least for me, if I'm interested in things. And I know a lot of the rest of the members probably found this helpful as well. But Yeah, I just want to say a huge thank you. Can we get like a round of applause, virtual applause, I guess, to Dr. Klimek for being able to speak and just kind of show us a little bit about everything. But yeah, all right. Well, thank you again. I'm gonna
Welcome.